This recording is one of the recordings that are part of the lectures covering neurophysiology. Previous recording, we addressed resting membrane potential. And so what we're going to do today is look at graded potentials. So graded potentials are short-lived changes in membrane potential. They're locally generated. They don't travel that far from their set point, but they're important in that you see on this picture that they could lead to what we call action potentials, which is a means by which we're going to be able to communicate. So one neuron going to the next neuron, or a muscle or a gland, the action potentials are needed for communication, and graded potentials can lead to an action potential. It's also a means by which, glands can release neurotransmitters. It's just these local changes in membrane potential. So as a quick reminder, before we go over some terminology, is remember if I have a cell membrane here, out here is the extracellular fluid, and here's the intracellular fluid, we have an unequal distribution of ions. You have a lot more sodium out here, and you have a lot more potassium in here, okay? Remember, the cell membrane is selectively permeable, so the ions aren't going to easily get across. You need some sort of channel to allow them to get across. And at rest, in a neuron at rest, we have a potential difference that's being recorded across this membrane. And it is minus 70 millivolts. So inside the cell is minus 70 millivolts compared to outside the cell, because we have a lot more negative charges in than we do out. So how are we going to disrupt that membrane potential? So what's going to happen, one of the things that can happen, is if I apply a stimulus that, say, opens up these sodium channels. So we'll say here's sodium, and I have a channel for it that I can somehow trigger an opening of a gate on that channel. So sodium is going to want to go into the cell because it wants to go down its concentration gradient. Plus it's attracted to all these negative charges that are inside the cell. So it wants to go from high to low. And what you would see as a result of this is this. You see this term referred to as depolarization. So depolarization, you see a reduction in that membrane potential. So you have less difference being recorded across that membrane, and as a result of those positive charges coming in the cell, that membrane potential becomes less negative. That stimulus is removed. What we're going to see is a return to membrane potential, and that's referred to as repolarization. So repolarization is when we restore resting membrane potential after that stimulus is removed. Repolarization also is what you see here. So we got to come and mention this term. So if I apply some sort of stimulus that causes, say, an opening of a potassium channel, well, if you notice, I have a lot more potassium inside than I do out. So potassium is going to want to leave the cell. So a loss of positive charges is going to result in an increase in membrane potential. The membrane potential becomes more negative as we lose those positive charges. And the term that we see as a result of that is referred to as hyperpolarization. So in a nutshell, I can apply a stimulus that can cause a reduction in membrane potential and refer to that as depolarization. I can apply a stimulus that results in an increase in membrane potential, and that's referred to as hyperpolarization. A return to resting potential is referred to as repolarization. Now, what you see here are transient changes in membrane potential. These are referred to as graded potentials. The reason why they call them graded is what you see here. So graded potential because the the magnitude of the change in that potential is directly related to the intensity of the stimulus. You see that change here from a weak stimulus, even greater change in regard to a stronger stimulus. So in the same regards, if you have a stimulus that causes hyperpolarization, weaker stimulus, you see that membrane potential coming down like this. Even stronger stimulus, even greater change in membrane potential. So over here in the left, you had some sort of stimulus that caused depolarization, which is a reduction in membrane potential. Over here is hyperpolarization, which you have an increase in membrane potential. Now, the significance of these two is graded potentials are significant because if they're like this one here, they can bring that membrane potential closer to threshold, and it's up here, it's up in this end here, to generate an action potential. If you have something like this, it's actually taking that membrane potential and bring it further from threshold, so you're less likely to generate an action potential. I want to look at this a different way too, just so you really understand what's happening in regards to that change in membrane potential. So I'm going to come back here to these pictures, and I'm going to erase them. So we'll say the first scenario where you had depolarization. I had said something that could cause that would be something that allows sodium to move into the cell. So sodium, say, moving into the cell, you're adding positive charges, and so you have a reduction in membrane potential. So we're going to do some just basic math. If I add those together, I got 3 positives and 5 negatives. When I do the math, that's -2, because these ones cancel each other out. So I have -2. If I add a positive charge, what do I have? -1. If I add another positive charge, that's 0. So I have a reduction in membrane potential. It's becoming less negative. Now over on the right where you have the hyperpolarization, so we'll come back to doing the +3, 1, 2, 3, 4, 5. So we got that -2 again. In this scenario, we said, okay, we're going to allow potassium ions to move across. I've opened some sort of channel, allow potassium ions to get across. So here, you're losing positive charges. And so what I'm going to do is I'm going to just erase. So if I erase that, instead of -2, what do I have? I have -3. If I erase another one, what do I have? I have -4. So I'm becoming more negative. I'm getting further from up in this area, and that's the area where I need to reach this magic term called threshold, which will be important in action potentials. Okay, so what we've done is we've disrupted the membrane potentials, and we did that by altering the permeability of the cell membrane to these ions. I have somehow opened up these channels to allow these ions to move across. And the reason why they move across is because they want to diffuse from high concentration to low concentration. So it's one of the reasons why they're going. So if you understand, you got to minimally remember the unequal distribution of ions that we have across membranes. So if I open up a particular channel, you know what direction these ions will move. So next recording we're going to look at is we're going to look at action potentials. But before we do that, one last thing is I want to emphasize is those graded potentials do not travel that far from the point of stimulus. They're going to kind of peter out. They're kind of they don't intensify. They kind of just don't travel along the axon. So the action potentials do, but graded potentials do not.